Today I'm here to showcase the latest addition to the Venice client library, the Venice fast client. Here's the agenda. We'll first talk about what is the Venice fast client, give you guys a quick architecture overview, what we have achieved with it, the results, the numbers, and then finally the road ahead. To fully understand the Venice fast client and its differences between the other Venice client libraries, let's rewind a little bit and take a look at the very first client library that we have, the thin client. This was already kind of introduced in the previous presentations, but just in case you missed it or you forgot about it, quickly go over. It's 2 network hops. We have the data bootstrapped in our Venice servers, and then a request comes in, goes through the Venice router, which will route to the correct server and then get your data back. So that's 2 network hops, and for a single get, gets you around less than 10 milliseconds for the P99 latency. And then a few years later, we introduced the Da Vinci client, which is the eager cache that bootstraps the data directly to local to the app, whether on an SSD or in RAM. And queries are made with 0 network hops that can get you, less than 1 milliseconds, where I think something like 200 microseconds for SSD, and then less than 10 microseconds for RAM. Now, users were happy about that for a bit, but then we started to have users that wanted lower latency, larger and larger batch get sizes, and for various reasons, they just couldn't find kind of the right place between thin client and the Da Vinci client. Here's a table that kind of illustrate those use cases where neither the clients can really get the job down. So for a thin client, the performance is not good enough, and the GC tuning. So most of our performance problems were actually in the routers. Our servers latency metrics has always been good, but then performance tuning like GC optimization for routers is getting harder and harder, especially in multi-tenant clusters where you have a mixed workload of single gets, batch get with different key size and all that stuff. Da Vinci client, on the other hand, will definitely meet the latency requirements. However, the data is either too big to be bootstrapped locally, or it's just hard to justify the operational cost and complexity introduced by Da Vinci client for some of the app users to kind of maintain and run Da Vinci client. And that's when we introduced the fast client, where we just bypass the router to get some performance boost, but we still have the data stored on the Venice servers. And then yeah, so you kind of it's like something in between gets the job down. We reduce the network hop to just 1, and then we can get less than 2 milliseconds for the latency for P99. Right. See, let's talk about the architecture. How does fast client work? So fast client talk to the Venice servers directly using R2, which I think stands for request response. It's just a library with abstraction for REST and RPC, request and response. But under the hood, it's just HTTP. And then it's using the same routing logic as Venice routers. So we do least loaded based on instance health monitor, which is the client's local view of what the state for each replica looks like. So for example, if we send 10 requests to one replica and 0 requests to another replica, we'll see that in the local view, and then the next request will send it obviously to the replica with less pending requests. But this is all good, but we need to know which server to talk to, and that's what we need the metadata in the Venice fast client, because we need the routing. For a given key, we need to know which replica, which server has the data. And on top of that, we also need to know a bunch of stuff like the versioning info, the schemas, so the user can still use this like a lightweight client. All they really need to know is the store name, and then with that they can query the Venice store. So we need to figure out what's their current version, the schemas, and all that stuff. So we have the metadata provider. So the job of the metadata provider is to get all these metadata to the fast client and keep it updated. So let's kind of split the metadata provider into two parts. One part is where to get the metadata. The second part is how we're getting it. So for where to get the metadata, we have, so the source of truth for all our metadata in Venice is stored in Zookeeper. And server already have a cache of those metadata for ingestion purposes. So we kind of just expand that on top of that, where all the servers in a cluster will have all the metadata for all the store in that cluster. This includes versioning info, schemas, and routing table. And we use our D2, which is a dynamic discovery service. Essentially, what it is just that you can have a service name, for example, like Venice, and you have for Venice servers, and you can have a bunch of hosts who announce to that service name, Venice server. And when you try to get in touch with this, with like a host that belongs to that service name, D2 can resolve that for you. It also does load balancing. So we use D2 to find the right server for a given store to hit its metadata endpoint to fetch the metadata. And then that takes care of where do we get the metadata from. And then in terms of how we're doing it, we have a local cache in the Venice Fast client, and we do this periodically. I think the default right now is set to once every minute, but this can be configured. We go ahead and fetch this metadata through this D2 client, gets it from the server, and then update the local cache. And all the during the hop path, all the actual requests are using the metadata from this local cache. So what happens when metadata is stale, right? Your servers can crash, routing table can change without you having the latest metadata. So we have error retry and instance health monitor to help us mitigate the impact of these route changes. They don't happen often, but when they do happen, what we do is that we'll send out another request and hit a different replica. And hopefully you don't have, like, if all the replicas are down at the same time, then it doesn't matter if you have the up-to-date metadata or not, you won't be able to get the request. But in most cases, only one replica is down, and it's also temporary. In the backend, we also quickly try to bootstrap like a new replica for you and all that stuff. We also have an on-demand refresh. So in that scenario, the initial couple requests will have to rely on error retry to avoid failure. But then the on-demand refresh will kick in, and hopefully it will be able to fetch updated view from Zookeeper. Because during like a real scenario when the node crashes, there's multiple delays. It's not just delay in like the Venice fast client metadata. Your Zookeeper view also will have some delay from the moment when the host is actually down to the moment where Helix, where Zookeeper realizes that, okay, that host is down, mark it off from our routing table and all that stuff. So we have to have error retry and kind of like the instance health monitor for that. And we also ensure that the metadata updates to the local cache are made in a race-free manner. What does that mean is that if the local cache is telling you that the current version is, for example, version 3, then I better have the routing table and all the information needed in order to kind of like make requests for version 3. I will never get to a state where I only have part of the data or only part of the update made it. So it's either all or nothing. And what does one cool kind of thing or side effect the metadata provider provides is it enables fast client to pick up backend configs. So one example of this we currently use is the batch get limit. So we limit the size the user can request. They can't just put like 10,000 keys in their one request. But this config is controlled by us from the Venice backend, and it's dynamically picked up by our Venice fast client. So we don't need to ask users to restart their client, or things like that. And this, we haven't tapped into this yet, but it will enable us to, like in the future, for example, we wanted to control feature ramps, turn it on for some users for a new feature, but keep it off for other features. We can do that through this config without the users actually have to do deployments or like restarts just to pick up like a new client config or something like that. We also have additional features kind of like added to the fast client for even better performance. We have long tail retry, the retry budget, where if a request is taking too long, we before we get a response back, whether it will succeed or fail, we kick off another one. And we only do this with some sort of moderation or limitation so that we don't cause any like cascading failures when the server is actually slow. We also do connection warming. Since we have the routing table, even before any request is made, we know exactly all the kind of like the possibilities where all the replicas that this client can hit. So we can perform connection warming ahead of time so that the connection will be warm when the user actually fire their first request. We also support speculative query. If you really, really want like super low latency, we can always send out 2 requests at a time, and whichever one is faster will give you the response. Okay, let's talk about results. So one of the first, not one of the first user of fast client in LinkedIn is T-Rex, which is our A/B testing platform. LinkedIn is data driven and T-Rex is like widely used. At any given time, we have tens of thousands of active experiments across the company. A single page load could be evaluating hundreds of them. Some experiments are evaluated in like a stateless manner, but there are also experiments that are targeted according to like characteristics of a member, like geo, industry, etc. And they require fetching entities from Venice. And these entities are stored and fetched from Venice. So with Venice Fast Client, for single get, roughly, I think this entity store is about 250 bytes in terms of their record size. We're able to get less than 2 millisecond P99, which from the 2 graphs, the top graph is the fast client P99 latency, averaging about 1.16. And the bottom graph is the thin client fast client latency delta. So it means it's the thin client latency minus the fast client latency for the same request. And we collected this data using like a dual read mode, which is something that we offered in fast client initially during its ramp. That we will fire a request for the same request, exact same request. We'll fire one using the fast client and fire one using the thin client. Whichever one finishes first, we'll use the result of that. And fast client always wins. So in this case, for the same request, thin client would usually take anywhere between like 2.5 milliseconds to like 3 milliseconds, which is like switching to fast client is more than like 50% reduction in terms of latency. And this is still a useful feature that we're keeping around because recently when we started adding the functionality for multi-get support for fast client, we actually used dual read to help us debug some weird issues that we were having multi-get. Another use case is the feed. As talked about during the previous presentations, feed is one of our recommender system, and basically tries to compute for the most relevant, the top relevant posts for users, and a lot of these computation involves running through ML models, which requires ML features that are stored and fetched from Venice. So these use case, they have a wide range of workloads, ranging from multi-get or batch get of 150 to 1,000 keys, with some stores in our regular clusters served using like SSD, and also some in our more performant large batch clusters, which are served through memory. And adopting fast client improved end-to-end latency by 30%. But this end-to-end it includes a lot of stuff. It's not just like Venice fetches. It also includes some additional computations, processing, and also it could be getting from like multiple Venice stores. Some are stored in our multi-tenant clusters. Some are stored in the in-memory clusters. Let's look at one specific example. So this is one specific store in a SSD cluster. And the top graph is the thin client P99, and the bottom graph is the fast client P99. You can see that they actually looks the same. And in fact, the thin client is slightly faster. What's going on? Well, actually, they're doing different workload. So this is one of the use case where, given a fixed latency budget, let's say you only have like 10 milliseconds or like 12 milliseconds, fast client can retrieve a bigger batch size than the thin client. So for those same latency graph, the average value size is all 200 and like around 200 bytes, but the key size is for thin client is only 64. But using fast client within the same kind of like time budget, we're able to retrieve like on average like almost 280 keys. So that's like a 4x, if not like almost 5x in terms of the amount of data we can retrieve within the same time amount. That's a good question. We did not collect that, but okay. So the question is, do we know what will be the latency for a thin client to retrieve the same batch size, meaning to retrieve 280 keys? I can tell it's definitely way slower. And in fact, in our multi-tenant clusters, sometimes we don't even support batch size greater than 150 because it causes a lot of GC and issues in the router layer. But yeah, I don't have the data at hand, but it's definitely slower. And we have some other use cases like SIS, our secure identity service, that use fast client single get. With the less than 2 millisecond P99 latency, they were able to get rid of Couchbase, which simplified their architecture, reduced maintenance burden, and improved overall stability. And hopefully we'll have many more use cases to come in the future. Now, finally, the road ahead. We have many kind of like improvements planned for fast client. So for example, we want to have the ability to talk to our servers using gRPC instead of R2, which will also bring support for protobuf. We also wanted to add Helix assisted routing for large multi-get, which will help us scale horizontally and improve the kind of the P99 or 99.9 latency for batch get use cases. We also want to add parallel processing or routing for large multi-get, because right now for large multi-get we are doing a key by key, and once you get to like 1,000 keys, 2,000 keys, or even like 5,000 keys, that will actually matter. That we're looking through like hash maps to figure out the routing like one by one. It would be great if we can parallel. We can spin up multiple threads and do that in parallel. Also, we wanted to implement a better long tail retry mechanism. Currently, the retry mechanism, the long tail retry mechanism, is configured on the client side, and also it's like a global config where it doesn't matter about your actual kind of batch size. Each route is retried after a certain kind of like timeout. So for example, if you set it for 10 milliseconds, then I'll kick off the long tail retry after 10 milliseconds. Doesn't matter if this request currently is asking for 100 keys, 1,000 keys, or just 10 keys, which for most of our use cases, their key size is relatively the same, but for some use cases, they can vary, right? So some requests might ask for 100, the next request might ask for 300 and stuff like that. Yeah, and we have many more. That's all. Thank you, everyone.